Hi everyone, it's great to be here. We have seen some really cool things and hopefully we can keep that going. My name is Uday Tatiraju. I'm a principal software engineer at Oracle, full stack engineer. My day job entails a lot of Java programming and the occasional JavaScript. I dabble in mobile programming. I sort of a jack of all trades, a generalist if you will. Let's get started and get the safe harbor statement out of the way. I want to emphatically state that the opinions expressed in this talk are my own, not that of Oracle's, and you know the rest. On to the fun stuff. Let's look at the agenda. I'm going to start with a demo of the finished product. So what we did was build an internal tool. It's a pre-commit tool using Vert.x, the JPMS, and since this is a distributed system, we also wanted to track it, and that's why we used open tracing. So I'm going to talk a bit about Vert.x, JPMS, open tracing, and how all of those come together. And so let's start with the demo. Like I just said, it's an internal build tool. It's a pre-commit validation tool, sort of similar to Jenkins or Hudson, but we had our own reasons to build this tool. It's Docker native, so it only runs on Docker. Enough said, let's take a look at the demo. All right, so this is the UI for this tool. A typical build tool experience, you provide connection details to a repository like Git or GitHub or Perforce, whatever. You define your build plan, the pipeline, so it can download the source code and build and test, things like that. But this is a pre-commit validation tool, not post-CI or a CI tool. What I'm going to do is create a really complex pipeline. Just kidding. I'm going to say hello world. All right, let's give it a name. And I can connect to a repository, but I'll keep this simple. This thing that you see at the bottom, that's the pipeline code. You can actually store that in a version control if you want. I'm going to save it, and then I'm going to run a pipeline. Let's go to the dashboard, take a look at the pipeline. I think it's done. Zoom in, sure. All right, so like I said, it's just a hello world pipeline. It's just printing, echoing hello world. But that's not what this demo is about or this talk is about. So just wanted to simply show you how the UI looks, and we can then talk about the backend stack and the technology stack and go into the details. I think that's pretty much all I have for the UI demo. One side note is that I used Oracle Java extension toolkit. It comes with a lot of pre-built UI components that you can use, so it was really fast for us to use it to build this responsive UI. Just a side note. All right, back to our presentation. So now that you have seen the UI, now what I showed you was I created a pipeline and started a pipeline, right? And the UI sent a message to the backend, which is the application layer. And it is built on top of Vert.x. Think of Vert.x as something similar to Spring, if you're familiar with Spring. I'm sure you are. And then we also made use of the new JPMS that was introduced in JDK 9. And we had some challenges using JPMS because it's a new thing, and there are a lot of open source libraries which don't yet support modular jars. So we are going to talk about JPMS, and since this is a distributed system, we have new challenges in terms of observability, monitoring, things like that. So we'll also touch a little bit about open tracing. Let's start with Vert.x. So I threw in a bunch of words, so I'll unpack those. Responsiveness. We all know what responsiveness is. It's the ability for the system to be able to respond in a timely fashion to incoming requests, right? And so if you build your application on top of Vert.x and follow certain patterns, you're guaranteed to provide a responsive system. Resiliency means that even in the face of failures, your system is still able to respond and be responsive. So Vert.x allows you to do that because of the way you design your system. You compartmentalize various aspects and distribute them so one failure doesn't bring your system down. Elasticity could be horizontal scaling, it could be vertical scaling, but Vert.x allows you to take advantage of the cores on a given system based on a reactive pattern. I'll talk about it in a bit. And then it employs a message-driven methodology, sort of the reactive manifesto, really. And so using Vert.x, you can take advantage of these principles while you build your distributed systems. Another cool thing about Vert.x is that it's polyglot. So we all know that JVM supports not only Java, but probably JavaScript, Kotlin, the new kid on the block, Groovy, and a bunch of other languages. And so Vert.x continues to support these languages. And the cool thing is that it provides idiomatic APIs, so it doesn't feel unnatural for you to try to use Vert.x in JavaScript, for example. And so you can mix and match languages based on your team's skill set or the task at hand. Let's say, for instance, you want to concentrate on the business logic, and you also want to experiment with Kotlin to reduce the verbosity of your code. By all means, go ahead and use it. Or you can use JavaScript. In fact, BuildMate uses Java and JavaScript. When I say JavaScript, I'm talking about the server-side JavaScript. They're using the Nashorn engine. And so, yeah, Vert.x is polyglot. It provides a lot of flexibility. And Vert.x is modular. When I say modular, I'm talking about the general modularization of code. The core library is pretty lightweight. Doesn't mean it's not powerful enough. In fact, it's the opposite. It provides a lot of modules that you can pick and choose based on your requirements. Let's say you want to use authentication and authorization. You can use that by picking a out-of-the-box module with the core module. You can connect to databases, Oracle database, MongoDB, what have you, and it supports an asynchronous way of communicating with databases. Everything about Vert.x is asynchronous in nature, and so it's a fundamental paradigm shift in terms of how we code, and it also brings some challenges because when you talk about JavaScript on the client side, we are all kind of familiar with the callback hell. And so Vert.x kind of introduces it, but at the same time, it provides a solution to deal with it, so it doesn't look too complicated when you look at a piece of code. Vert.x provides ways to connect to other eventing and distributed messages. For clustering, it uses a plug-and-play approach. You can use Zookeeper, you can use Hazelcast, you can use Ignite, or you can roll your own one. You can create REST APIs. You can use the OpenAPI 3 specification, give it to Vert.x, and Vert.x will generate the REST API along with the validation. Or you can code your REST APIs on your own. So a lot of flexibility. That was my point anyway. So the central aspect of what makes Vert.x awesome and responsive is this thing called vertical. It's loosely based on the actor model, where actors classes communicate with each other using messages, and these actors in the Vert.x world are called verticals. And so one or more verticals will actually make up your microservice. You can deploy them. In Vert.x, there's no concept of a application server like Tomcat, Jetty. I mean, you can use it, but you don't have to. So it's very lightweight. Probably makes much sense if you use it in the Docker world or Kubernetes world. It makes much more sense to go with a framework like Vert.x. And there is a central event bus. That's how messages are passed across these various services. And Vert.x manages the event bus. So you don't call Vert.x. Vert.x calls your services based on the incoming messages. Event loop is also not a new concept. I mean, if you take the browser, for instance, the engine listens to various events like a click event or let's say a mouse drag event, right? And based on the event and the registered handlers, it calls those handlers, right? Similar concept here. A vertical is essentially providing certain handlers, and it's asking the Vert.x, which is the engine. And whenever a message arrives at a specific arbitrary address, the message is passed on to a particular service. One thing, though, about a single event loop is that it's attached to a single thread. The affinity is to a single thread, and so you can't really take advantage of multiple cores. And Vert.x solves this using what it calls a multi-reactor pattern, essentially creating multiple event loops based on the number of cores. You can configure it. And so within a single system, you can scale across the available cores. Enough talk. Let's look at some code snippets here. I have two code snippets. On the left-hand side is the Java code. On the right-hand side is JavaScript code. Kind of looks messy. I thought I figured that out, but apologize for the messiness. So if you look at the right side code, the JavaScript vertical, what we are doing here is creating a hello world server. It's listening on port 9000, and it's essentially sending out hello world from JavaScript to every request that comes in. It's as simple as that. And on the left-hand side, a similar hello world server for Java. Same thing, listening on port 9000. You create a HTTP server. You register a handler. Since this is a simple example, we're not really making use of verticals as much as we want to. And so same thing, respond to incoming requests with hello world. Let's take a look at a more complex vertical example. And like I said, vertical is nothing but a class which acts like an actor in the actor model. So it registers to a message, and it waits for messages to come in, and then it does some computation, store it in the database, or do whatever, right? So you can extend the abstract vertical class that Vert.x provides, or you can implement the Vert.x interface, or the vertical interface. And these verticals are then deployed by the Vert.x engine. And Vert.x makes heavy use of features. Like I said, it's asynchronous, so there's a change in the way we program. You have to make heavy use of Lambdas if you are using Java, of course. And so what's happening here is that we are going to get hold of the event bus that's provided by Vert.x. And then we are going to say, hey, Vert.x, whenever there's a message on this specific address, which is a made-up address, it says workspace : setup, send me that message and I will handle with it. And so I have some comments there. You do some work, and then you can fire a message. So that's what's happening here. So you register for a message. Incoming messages are sent by Vert.x to your vertical, which can be, I mean, this could be a microservice on its own and be deployed, but that would be an overkill, obviously. But a bunch of verticals together in a single JVM instance can then make up your service. And so when you distribute it, you are dealing with the reactive manifesto in terms of being responsive, resilient, and all that stuff. So that's a quick overview of Vert.x. And if you recall, in the technology stack, I said we built Buildmate on top of Vert.x, and we leveraged JPMS. JPMS is the new platform modularization system introduced in JDK 9. Actually, it was scheduled to be released in, I believe, Java 8, but that didn't happen because of Lambdas and streams and because of the complexity that was involved in actually creating a generalized modularized system, right? So finally, in September 2000, we got the JPMS. Its code name was Jigsaw. For one, I'm really excited about this. Granted, we do have OSGI, which deals with hiding your packages and other things, but we never had native support from the platform itself. And finally, in JDK 9, JPMS, through JPMS, we have that. So what is a module? in generic terms, I mean, we use modularization everywhere throughout the hardware and the software stack. But specific to the JDK, a module is essentially a jar which has some extra decorations to it to specify or publish its public contract, meaning its APIs or its classes that the consumers can use. And also, we have to provide or specify the dependencies that the module that you're building has on additional third-party or the platform modules. Other cool thing about JDK 9 release is that the platform itself was modularized, so this opens a whole new bunch of possibilities in terms of creating custom runtime images. Now, if you are using JDK 8 or previous releases, we all know that the JRE is one big thing. Granted, there are a couple of profiles that you can use to reduce the size of your runtime engine, but you can't really squish it down any further. But with the modularization of the platform itself, now you can say, I just want to use X, Y, and Z modules, and done. You have a very compressed, small module, and in this container world, that makes a lot of sense. So that is possible because the platform itself has been modularized. And all modules have to rely on the base module. In fact, this is an implicit requirement, so even if you don't specify it as a dependency when you're building modules, it still works. And all of this is possible with the introduction of a new construct called moduleinfo.java. Right? Like I said, you specify, or as a developer, you specify the public contracts, the services or the classes that you are providing. And you can also specify the dependencies. Actually, let's dig deeper. So a new keyword has been introduced called module, and followed by, in my example, I have used the reverse domain naming convention that we use to describe packages. You can employ a different strategy. A new keyword called exports has been introduced. That is how you tell the consumers of your module that these are the packages, these are the classes that you are exposing for consumption by third party, and you are hiding the implementation details. Another keyword is the requires word. That's how you specify the dependencies that you have in order for your module to work, right? In this case, I'm specifying that the domain module depends on Java base, and it also depends on the Apache Commons library. And so for the moduleinfo.java to work, obviously we need some additional enhancements to the existing tools. New command line options have been introduced, like JLink. Previously I was talking about creating custom runtime images, and so JDK provides us with a command that allows you to build the custom runtime image using JLink. And the Java-C and other command options have been enhanced. Let me quickly walk you through the options, or some noteworthy options. For Java-C command, module path has been introduced. This is where you specify the dependent modules when you are building a module. So let's say I'm building a domain module, and I rely on the Apache Commons module, and it's sitting somewhere within your file system. You have to use the module path to specify the file system. Obviously, we're not going to hand code the Java-C commands. We're going to use Maven or Gradle or something else. And similar options have been introduced in the jar command. Sometimes you might want to know the module name. You can use the describe module option too, and it will print out the details of a module. For deploying for runtime, the Java command has been enhanced. Similar options have been introduced. The module path to specify where your modules live. List modules will tell you the list of modules that your runtime application needs. And the most important thing is the -- module option, where you actually specify the module and the main class within that module that's going to kickstart your system. I talked about modules, And it's all fine if you're creating new modules, but that's not the case, obviously. We have to rely on open source or proprietary modules. There are millions of them. So how do we go about using those modules while still moving forward with the JPMS? Well, we have this concept called automatic modules. There are two ways to deduce the automatic module. One way is to use the automatic module name entry in the manifest file. Every jar has a manifest.mf file, right? So you can append this entry within your jar, and then the JDK knows how to use this module. And this is called a non-modular jar, but you can still make use of it using the automatic module name approach. Let's take a look at an example here. So I'm going to pick the Apache Commons Lang library again. So the name of the jar is commons-lang3 the version name .jar. But the good folks at Apache decided upon a module name. And even though the jar itself has not been modularized, we still get to use it using a new name called arg.apache.commons.lang3, right? Even though the jar name is different, we can use this because the manifest entry contains the actual module name. And so they have time to now to modularize their jar, but in the meantime, we can move ahead and use the Commons library. But that's not always the case. Some library authors don't have enough time, or they're not really bothered about JPMS. I'm not saying that in a bad way. So there is another way to deal with it. Java provides a simple algorithm to deduce the automatic module name, and that's to use the name of the jar itself and remove the extension. So you drop the .jar, and then if there is a version, it will drop that as well. And the remaining hyphens would be converted into dots. But in this case, there is nothing else. So the deduce name becomes P4 Java. And on the right-hand side there, I specify how to use that. So it requires P4 Java, that's it. And IntelliJ and Eclipse and other IDEs do have support for JPMS now. So it will actually let you know how to use a non-modular jar, which is pretty cool. All right, now that we have seen the JPMS, how to define the module info class and the command line options, let's take a look at how buildmate runs. This is the command, the runtime command. You're specifying the module path. So the lib folder has all the application modules that we built, and the jmods folder has the platform modules. And then you're specifying that you want to start with the buildmate.node module as your primary means to enter your application, and the node launcher is your main class to run the application. But we'll see a problem when we run the system, and this is because a lot of libraries out in the world make use of internal details of the JDK. And so what it's complaining about here is that P4 Java is trying to make use of a class which is hidden from the public. So it's an internal implementation detail, and with the JDK 9, like I said, since it has been modularized, you can't use those classes. But you can't just say you can't use and be done with it. So Java has a way around it. And in order to figure out which class is using which internal library, you can use the enhanced JDEPS tool, which is an analyzer. It will go through the jar, read the byte class, and figure out what is going on. Using the JDK internals option, it actually allows you to concentrate on the JDK modules only. And so it's saying here that P4 Java is trying to use the get property action thing, that's the class, and that's an internal implementation detail. So. And a nice thing is that it actually gives you suggestions on how to deal with it. And in this case, the suggestion is to replace it with a public equivalent of the getProperty action class, and that has been available since Java 1.1. But since we are not the authors of the Perforce client library, I can't do that. So I'm going to say, hey Java, thank you very much, but take a chill pill. Let me allow to use P4 Java for now, And so the add opens does that for you. So add opens, and then you're saying, okay, I know this is an internal implementation detail, but for now, give P4 Java access to the internal implementation. Once you do that, you're off, and you have Buildmate up and running. And I said, when I talked about Vert.x, I said that it's a framework that allows you to distribute your application across JVMs, whether it's running on a Docker container or on a VM, doesn't matter. But that brings some challenges, and this is not something new. We all know that when you build distributed systems, tracing and instrumentation, monitoring, those become difficult. And how do you deal with that? Many vendors have found solutions, but the only problem is then you're tied to a vendor-specific implementations. And open tracing solves that problem. It's just a vendor-neutral, platform-agnostic API contract. That's it. Whether it's Java or Go or JavaScript, it just provides you with an API, and you have to find a concrete implementation. But then using that allows you to not get tied to a specific vendor, but very simply change the implementation aspect of tracing. And it's really useful when you are dealing with production issues in a large distributed systems. Fundamental concept within a distributed, open tracing is the trace. A trace tells you a story about the request as it flows through your distributed system, right? In this example here that I have, the client-side JavaScript sent a message to the API gateway asking it to start a pipeline. And a bunch of things are happening behind the scenes. And in a monolith, this is all very easy. But when you have a distributed system, things get a bit more complicated. So in the case of Buildmate, the API gateway is going to send a message to the authentication vertical, which is nothing but a simple service, which is listening for messages. Looks at the header and decides whether or not the caller is authenticated and authorized, right? And once that's verification is done, asynchronously we get a message back saying authorized or not authorized. And based on that, another message is sent by the API gateway to the resource vertical, and it could be doing something like creating a build object, saving it in the database, and providing a message back. And then the API gateway will talk to the engine vertical, which is going to spin a container and build your application. So, but if you look at it, 6 and 7 happen almost immediately after each other, and that's because we don't necessarily have to wait for the pipeline to end. And so we send a message, we forget about it, and send a 202 response back to the client. And that's what a trace is essentially tracking. It's tracking the progress of a request once it hits the server and passes through the various distributed systems within your internal network. Of course, this is a bit of a simplification. Things would be much more complex. And so a trace is actually a directed acyclic graph and of spans, right? What is a span? A span is a logical unit of work. So it's a made-up operation name. So in my example here, I'm saying that start pipeline is the main span. And so what you see here is actually the same thing that I show here, but in a better way, right? You have a time graph, you have a span flowing across the time axis, and then you have child spans doing parts of the work. So authentication span, the create build span, and sending a message to the event bus to some other system, and then finally a 202 response. So when you are trying to figure out the issue within a production system, then you can go to the tracing to figure out what, for example, if you're trying to see which one takes a lot of time, this span diagram would help, right? But open tracing doesn't provide an implementation. You have to get one, and a lot of vendors are now implementing open tracing natively, and Yaeger is one such implementation. I think it's provided by Uber, And they handle billions of spans per day. So it's a very powerful, highly scalable system. It supports multiple backends, Cassandra, memory, what have you. And the cool thing is that it provides a web UI where you can actually go and look, search for traces, or dig into spans and see how the system or the request is flowing through your distributed system. Obviously, you need to configure Yaeger. And the global tracer that I show here is actually coming from OpenTracer. So it's a public API, and you have a concrete implementation. And you're saying, I want to use Yaeger as my tracing implementation within your distributed system. So if you're writing a lot of microservices, you can, instead of using a global tracer, probably use a dependency injection mechanism to configure your tracers. And one cool thing about Yaeger is that there is a way to control the sampling rate. Obviously, in production, you don't want to track every request that flows through your system. And so there are multiple ways in which you can configure the tracer. Some of them I outlined here. There's a way to remotely control the tracing or the sampler, constant on or off, that's it. I used it as an example here, and also used it for the demo where every request is tracked, but you don't want to do that in production. And then there's a way to rate limit the tracing. And you can say, for every second, I only want to trace 10 requests. Or you can roll up your own and decide on how to trace. But of course, that kind of adds additional complexity to your system, and you don't want to overburden your system just for tracing purposes. And let's go back and look at the demo of the Yaeger UI. And within BuildMate, we have a link to the tracer. And so you see that it has a couple of services, or more than that, actually. So we have BuildMate Node 1, Node 2, and server. These are the verticals, essentially, that have been deployed. And so each node, or each vertical, or a bunch of verticals, actually, does a specific piece of work. And so you can track them down and see what is happening within those nodes. Actually, let's see what happens with node 1. We have a span here. Again, all of these are just arbitrary names. You can come up with whatever you want to. BuildMate node 1 is the name of the service, followed by the span or the trace name, which is build_flow. It can be much more meaningful than that. And then you see that there's a timeline access, and your spans are distributed across the parent span, which is the build flow. There are certain steps happening here. These are all the messages going internally within the cluster. And you can drill down. You can tag your spans with with more information if you want to. For instance, let's see what I have here. I added a build ID to it. That way I can track if something is wrong within my system, or with a specific build. I can do that. I can drill down and see what's happening, so, which is very cool. I think that is all I have. So all of these come together, and that's how we build BuildMate, using Vert.x, using JPMS to modularize the code, and we used open tracing to track requests that are going across the distributed environment. I think that's all I have. Yep. Thank you.